Hello my warriors, hello my dear Enlites. I hope you guys can hear me. Welcome Ultra Legends. Welcome aboard. Yes, this is Shreyas here, your physics master teacher at Vedantu going live. And today's session, like you have seen in the title, it's all about the important properties of a conductor and also the fields, potentials, their relationships with each other. And yes, we'll end the class with dielectrics and some awesome questions on that as well. So the chapter is covered into parts, and many of you are also aware that I have already covered this chapter last year in the Pathfinder series. So I highly recommend you watch the Pathfinder playlist, which is available right now on this channel. And these lectures, the Ultra Legend series, will act like a support in addition to those lectures, which will help you improve your concepts towards JEE as well as NEET. So welcome all the NEET and the JEE warriors. It's time to study conductors as well as dielectrics with me, Shreyas, your physics master teacher. And before we begin the class, do not forget to smash the like and the subscribe button because it means a lot to me. Hello Purushottam, hello Srivatsan, hello Mukund. Welcome guys, welcome to the channel. Good evening. So I had to shift the class today at 4 o'clock, but I hope in case you are not able to attend it, you will watch it in the recorded way as well. So let's start with a quick recap of what we have done till the last lecture. And mainly, I just want to recollect field as well as potential. See, field, if you recollect, field is something which is produced by a charge everywhere. Any charge produces field around it, and field is defined as the force which acts per unit test positive charge, right? This is how the field has been defined, and the unit of field is Newton per Coulomb, if you recollect. And the field due to a point charge is just given by K, which is your 1 by 4 pi epsilon naught, and then you have the charge value divided by the distance square, right? I hope everybody remembers this. Hi Omeshwaran, Subhash, welcome Bacha. Hello Anushri, hello Pavan. Good evening, my dear warriors. And when you have a positive charge, it creates a field outwards. I hope you recollect this. And when you have a negative charge, the field is created inwards. This is how it works. Wherever the field lines are crowded, you will see that the field is strong and field lines cannot intersect each other. Field is a vector quantity, always in the direction of the force on the positive charge. This is what we have discussed. Similarly, if there is a field is basically, I know that every charge has its presence felt around it through this field, because the moment you place some charge, the charge is going to experience a force. So that's how I know that there is a field. That field is there even without other charges, that any charge produces that, presence being felt around it. That's how it is. Okay. Yep. Advanced problem solving session on Harant is asking on capacitors. Well, I will definitely conduct one. In fact, I'm planning to do it for all the chapters, not just for capacitors. So stay tuned, Bacha. I will do it. Definitely. Hello, Sai. Awesome. Pavan, in case you have 84 percentile, I would suggest you please keep your backup options ready and also prepare for taking a drop as well in case you want IIT only. Hello, Shafika. Similarly, you have potential. Potential was defined, recollect, potential was defined as the work done to bring a charge from infinity to that point per unit charge. This is how it was defined, per unit test charge. And the formula for potential due to a point charge was given by kq divided by the distance. And recollect, any charge which is there, it produces equipotential lines around it. These are equipotential lines V1, V2, etc. So it tells me that around this point there are potentials created which are similar. At all these points on this green line, the potentials are same. At all these points on the green circle, the potentials are same. But this point and this point, they have a potential difference between them. So these 2 points obviously will have some kind of a difference in the potential. I hope this is clear. Magnetism will start after current, electricity and capacitors very soon. I'm planning to complete most of the things by November, say. Okay, by November, yes, your 12th standard Ultra Legends will be over. Yep. So I'm going to conduct an advanced problem solving session next week also, I think on Tuesday if I'm not wrong, Tuesday or Wednesday. So make sure you're a part of it. You will learn a lot of these things, lot of multiple concepts, lot of new ways of solving questions, especially in the advanced sessions, even if they are meant for 2022. Okay, so this is a quick recap. Make sure you are a part of the Telegram channel. The link is there in the description box, or you can even scan this so that you do not miss any updates and also get the PDFs along with the homework solutions. Okay, so let's begin. Hello Aishu, hello everyone. Good evening, join in. Now, I want to start the class with the relationship between field and potential. Can somebody tell me in the chat box? Do field lines travel from somewhere to somewhere, potential wise? Do you know where field travels? From which potential to which potential? I am very good, King of Kings. I hope you are doing great too, because you're already the King of Kings, I'm pretty sure. So, one thing which is very important that you should know is that if you have high potential somewhere and if you have low potential somewhere, the electric field always travels from high potential to low potential. Everybody, remember this. Yes, very good Aishu, and very good everyone who are answering. Everybody should know this, that if I take a ball, it will always try to roll down some incline or a hill or from a surface. Everything in this universe wants to lower its potential energy. So does field. Field will always try to push the charge in such a way that it will push it from higher potential to lower potential. That's a common thing across all the systems in the universe. Not just that, there is one more interesting thing. If you have an equipotential line, this is equipotential line, or basically surface, whatever it is, you will notice always the electric field lines are going to be perpendicular to the equipotential surface. E field is always going to be perpendicular to the equipotential surface. There is a simple reason for it. Just imagine if electric field was not perpendicular, electric field will have some component in the direction of the potential. If electric field has a component in the direction of potential, that means electric field will do work in the direction of potential. That means electric field will do work in the direction of this yellow line. How can you do work? On this line, there should be no work done when you take a charge. Remember that. Potential energy does not change on that yellow line or that equipotential line. So if the field is doing work, obviously the potential energy will change, potential will change. So it is incorrect. So hence, field lines are always perpendicular to this. Are you getting it, my warriors? Yep, these lectures will be helpful for advanced. I will be taking advanced classes exclusive also. This right now is for both JEE and NEET. Exclusive advanced classes will also come. Football player, my name is there right in the title, session title. What is the proof that field lines will not intersect, Aishu? Simple. If see, what does the tangent give you? The tangent gives you the direction of the field, correct? The net direction of the electric field on any charge what you place, like the test charge. If the field lines intersect, that means there are two fields at the same moment. But how can you have two fields, net fields, not individual fields? They are net electric fields at the same moment. You can only have a unique direction of the electric field, hence they cannot intersect. I hope that makes sense. Next advanced class, Space Scientist, is on Tuesday or Wednesday. Stay tuned. Now there is another interesting thing which happens with respect to field and potential. Let me show that to you. So let's say, for example, the field lines converge, something like this example. Okay, the field lines converge. Here I will say that the field is strong. So this is an area where the strong field is there. And I will say here there is obviously weak field. There is weak field because the lines are a little bit far away. Guess what? The equipotential lines are not as closely packed as they are over here or there. The closeness of these equipotential lines also changes depending on the electric field's strength. Wherever the field is strong, the force is strong, the work done by that force is also strong. If there is more work done by that electric field on that charge, that means the potential will change very quickly. So potential changes quickly where the field is strong. If the field is weak, force is weak, work is small, so potential will change slowly. So you will see this. Yep, this is a non-uniform field, and what you will see is here the potential lines will be very closely packed and they will slowly start going away, and maybe they will go like this. Yes, the closeness of the equipotential lines will be different. You can see this is V1, V2, V3 and V4. So the rate at which the potential changes. So potential changes faster where electric field is strong. Where electric field is stronger. Is basically stronger. I just mentioned this word. Stronger. Very, very important. In fact, there is a relationship for this. Very easy relationship. I'm pretty sure you would have seen this relationship. Let me just go back to the recap slide. Back in the 11th grade. Let me know if you have seen this. Force and potential energy change is related by minus du by dx or minus du by dr. Have you seen this? Have you seen this? Or in general, it is any rate of change of distance with respect to distance. So I can just put dr. It could be x-axis, it could be y-axis, it could be z-axis, anything. So the force produced by that conservative field is the negative rate of change of the potential energy. So force per unit charge is field. Energy per unit charge, basically work per unit charge, is also nothing but potential. In fact, the formula comes out to be like this. Observe it now. The electric field at any point is actually given as negative du by dr. This is the formula. And why does this minus sign come? What does this minus sign stand for? Interesting. Negative sign, this is not u, this is v, in case it is not very obvious. Let me just write it like this, minus dv by dr. So this is dv by dr. Okay, E is minus dv by dr. What does this minus sign stand for? The minus sign stands for the fact that field always goes from high to low potential. That's all. That is what that minus sign says. If the potential increases, field will be opposite to the direction of the increase. Field always goes from high to low. dv by dr is also referred to as the potential gradient. Many people would have seen this word. This is also called as the potential gradient. Gradient means rate of change of something with respect to the distance. So potential gradient stands for the rate of change of the potential as you move from one point to the other. So like you can see here, the field is strong, so the gradient is strong. That means the potential changes very quickly. Here the field is weak, E is less, so you will see that the potential does not change as fast as you expected. As simple as that. How can non-uniform field have equipotential surface? Non-uniform field can also have equipotential surface, just like this one over here. Just look at this. Is this field uniform produced by a point charge? No, right? It is non-uniform because the field strength decreases as you go away. Does it have equipotential line? Yes, it does have equipotential line. So there is nothing like a non-uniform field cannot have equipotential line. Equipotential line just tells, okay, these points have the same potential on that or in that region. That's all. In fact, if you draw perpendiculars to that, you will get the electric field at that particular point. I hope that is clear. Yeah, I hope this is fine. Everybody with me? No, this is not the first class, Santosh. This is probably the second or third class of the 12th standard. In fact, let me also show you guys. These are the lectures that you should be watching right now in case you are not aware of it. So as you go on our channel, go to playlist out here. And once you go to playlist, right, I want you to go through these lectures. JEE NEET class 12th PCMB. You can see, one second. Yeah, JEE NEET, where did it go? JEE NEET class 12th PCMB. Yes, that's over here. You can see physics playlist, Pathfinder 12th physics playlist for both JEE and NEET. Open this up. I have the entire physics playlist out here right from the first chapter, like you can see, right, for electrostatics, Gauss law, everything. These lectures you have to watch. I am doing not the exact same thing, I am doing something additional to that which will add value to these classes. There's no point doing the same thing. I want you to go through this. All the classes are there, right till semiconductors and communications. Okay, some of you might have seen this, but some of you might be new. That's why I'm showing this to all of you. Great. Okay, awesome, awesome. Now let's solve some questions based on this. I have put up the pointers. This will be also available to you in the Telegram channel. Remember, even my handwritten notes are available. So let's say, for example, let's take a small example out here. Imagine the potential is basically x cube volts, and then the question is, what is the field? The question is, what is the field? Here is what I am going to do. I will say field is nothing but negative dV by dr, but here potential is a function of x. Potential changes with the x coordinate, so I should differentiate voltage with respect to x. So this will be nothing but minus d by dx. The voltage is nothing but x cube. The derivative of x cube is nothing but x square, 3x square, correct? So this is going to be the field, but this is entirely going to be in the x-axis. So the field is minus 3x square. I hope everybody agrees to this. Let's take another example. Okay, let's take up another example. So let's say the voltage is given as y square volts. Y square volts, example. And then they again ask you what is the field because of this potential. Here is what I'm going to do. Well, field is negative potential gradient. Here, potential is a function of y coordinate, so I should differentiate voltage with respect to the y coordinate, of course. So minus d by dy, voltage is nothing but y square. The derivative of y square is nothing but 2y. So that's what is going to give me the field, but this field is not in any random direction, it's in the y-axis. What's the purpose of doing this? Now you will understand. Observe this carefully now. Observe this carefully now. Imagine that they tell you that the potential is given by x cube plus y square volts. X cube plus y square volts. Now what will you do? Now what will you do? No, Tamil, magnetism will come after this, but in Pathfinder I have completed magnetism long back. So you can watch the lectures if you want to. Those are always available for you. What will you do now in this case? Think. Now you cannot differentiate with x or y, but collectively, but you can differentiate it separately to find the each component separate. So if I find dV by dx with negative sign, that is only going to give me electric field in the x-axis. So when I differentiate this, minus d by dx of x cube plus y square, this is going to give me Ex. I am just trying to say, hold on, y is a constant, I am just differentiating with x. Everything apart from x is a constant. Just treat y as a constant, the derivative of a constant is 0, so it will be nothing but minus 3x square. Similarly, if I do minus dV by dy to find out the electric field in the y direction, I will say minus d by dy again of this x cube plus y square is equal to Ey. So I am just going to get the value of Ey as minus 2y because x is a constant. When you are differentiating with y, whenever there are two or more variables, ignore the other variables, treat them like constant, only differentiate with whatever is there below over here. So what I will get is electric field in total is, the x component is this much, so minus 3x square I cap, and the y component is this much, minus 2y j cap. This is what I get. So this is how you can solve problems which involve multiple variables. Whenever multiple variables are there, find the derivative with respect to x and y separately and then combine them in the end. That will give you the easy solution. Let's take up one more question so that you get a hang of it. Just imagine your potential is given by 3xy raised to 4 volts. And then they ask you, find the electric field. That is the question. Let's try to do this question. So first, I'm just going to find the value of Ex. This will be negative potential gradient with respect to x. So it will be minus d by dx of this 3x y raised to 4. Everything is constant. like 3 is constant, y raised to 4 is constant, only terms of x will remain inside. Dx by dx is 1, so hence it will be minus 3 y raised to 4. That is the value of your Ex. Similarly, what you're going to do, you're trying to find Ey now. This will be nothing but minus derivative with respect to y only. So minus d by dy of this 3x y raised to 4. Now 3 is going to come out, even x is going to come out. It will be only the derivative of y because downstairs you have y over here. So derivative of y raised to 4 will be 4y cube. 4 3s are 12. So minus 3x y cube. That is your electric field's y component. So now the net electric field, what will be the net electric field? It will be this component, which is minus 3y raised to 4 I cap, and this will be the y component. So minus nothing but 12x y cube j cap. This is your final electric field vector. This is how it is going to be. Is it a good idea of combining NEET and JEE for JEE Aspirants, sir, and a number of attempts of JEE Mains? Well, see, I'm not sure what the final proposal is, so it's too early to comment whether it is good or bad. I would be waiting for their final proposal. But for JEE Aspirants or NEET Aspirants, level-wise, I feel physics and chemistry will be easy. Those who are going to give engineering, for them maths will be tough. Those who are going to give medical sciences, for them biology will be tough. I think physics and chemistry, they will keep it easy or moderate. They will not mess it up for NEET students, nor will they make it very low for the JEE students. But I feel they should probably have a separate entrance test or maybe a separate section in the paper for IITs or for such institutions where JEE advanced kind of questions are expected, which will not be expected to solve by the NEET students. So that's what my personal belief is. I don't know what is going to happen. All right. So I'm pretty sure that they will have more attempts. At least 2 attempts will be there, not 1 attempt. Okay. How about solving this question, my warriors? Come on, try to solve this and let me know the answer, the correct option in the chat box. 2 plates are separated by potentials minus 10 volts and 30 volts. If the separation between the plates is 2 centimeters, then the electric field between them is how many? How many volts per meter? Yeah, let's try to do this. So think about 2 potential lines, one over here and one over here. These are minus 10 volts and this is plus how many? 30 volts. These are your equipotential lines. Naturally, electric field has to be perpendicular to it. So electric field will be like this. In fact, this electric field will be uniform field, and there is some distance between them, that is basically your 2 centimeters. Great. Now, if you recollect this formula, E is equal to minus dV by dx. This formula, the gradient dV by dx, gives me the instantaneous rate of change of potential with respect to x. Instantaneous rate. Just like instantaneous velocity is dx by dt, or instantaneous acceleration is dV by dt. Come on, think about it. When velocity is constant, isn't instantaneous value and average value both same for velocity? Same way, when acceleration is constant, won't instantaneous acceleration and average acceleration be the same? Here also, the field is uniform. So if this field is same throughout, won't the instantaneous value be also equal to the average value delta V by delta X? Everybody agrees with this? I hope this is clear. Awesome, awesome. Now, what is the magnitude of this? I'm not interested in the minus sign and all. So let's just find the magnitude of the field, and that will be delta V by the distance. That's all. So what is the change in the potential from here to here? Minus 10 to 30. What is the change, guys? Come on. Is it 20? Is it 40 or something else? Come on. Football player saying B. Okay. Let's see whether it is B or not. Delta V, what is it? Is it 20 or is it 40 or is it 30 or is it 10? 30 minus of minus 10. Be careful. The answer will be 40 volts. And the distance is 2 centimeters, so that is 2 into 10 to the power minus 2. So that is nothing but 20 into 10 to the power 2, which is nothing but 2000 volts per meter. That is also the unit of field, by the way. Okay, so we have it as option A, not B. Yes, the A is the correct answer. It's not option B. A lot of people think 30 minus 10 is 20. So 20 by 2, that 2 gets cancelled, and many people mark it as option B. No, it is not 20 volts. It is, remember, 30 minus, this is final, minus initial, minus 10, which is going to make it 40 volts of difference. A lot of people make that silly mistake out there. Okay, so moving on to the next question coming up on your screen, and here it is. Let me write an equation out here, and let's see how many of you can do this. The electric potential at a point xyz is given by, let's say the equation is 4 times of xy plus z, this is z, minus 7 volts. This is your equation. The question is the electric field at any given point will be how much? Let's try to do this. We have to differentiate voltage with respect to 3 variables out here, x, y and z. All the 3 coordinates are there. So let's start with the Ex component first, which is negative dV by dx. So negative, the voltage is nothing but you know, your 4xy plus z minus 4. Remember, I'm differentiating with x. Y and z will be assumed as constants when I'm differentiating with x. So it will be nothing but, so for the 4xy term, 4y will be constant, derivative of x will remain with respect to x, z's derivative with respect to x will be 0, constant, and 4's derivative will also be 0. So hence it will be just nothing but 4y with negative sign. That is the value of Ex. Everybody fine till here? Similarly, let's try to find the value of Ey component, which is minus d by dy of this entire thing, which is 4xy plus z minus 7. Now y is the variable, z and x are constants, so minus 4 will come out and even x will come out. Only thing remaining will be dy by y, and derivative of z will be obviously constant, this will be also constant, so 0, and here I will get this as minus 4x. This I'll get it as minus 4x, right? Hello Gitendra, welcome, hola. And what about the z component, which will be minus d by dz of this entire thing, which is 4xy plus z minus 7. Now 4xy, entire thing is constant, so it is 0. For z, x and y both are constants. So here I will have minus dz by dz, minus becomes plus, you can call it as 0 again. So this will be nothing but minus 1, of course. So finally, what is the net electric field? The net electric field will be this much, minus 4y will be the I component, this much, minus 4x will be the y component, and minus 1, that means minus k hat, will be the k hat component. So that is that many volts per meter. Is that fine, my warriors? Minus 4y. It will be minus 4x, bacha. Football player, not plus 4x. I think you missed that minus sign over there. Be little bit careful. And minus k hat. So that minus 1 will be there, not plus 1. Be careful about that as well, because this is plus z. So because of that minus sign here, there will be an additional minus sign. Okay, so be little careful with the calculations, otherwise it is fine. Sign especially, because options might be there which are confusing. Now let's move on to some conductor properties. Okay, now the most important properties of a conductor will be where if you have a conductor and if you charge it, if you charge a conductor, let's say you make it negative charge, these negative charges will not love each other. Okay, so Godwin, you can do one thing, you can just contact me, that will be better. Okay, because I can't vouch for somebody calling you. It's better that you contact me on my Instagram handle, that's captain_Shreyas. Okay, that's better. Okay, now when these negative charges come up on a conductor, what you should do is think, what will these negative charges do to each other? They will repel, so they will try to move away, so they will try to spread as far as possible, and the maximum they can do is come up on the surface. Same thing happens to the positive charges or even the negative charges. These charges don't like each other, so they always come up on the surface. So the moment you have a conductor and you charge it, you will see the charges will always be on the surface. The charges try to spread So the charges spread as far as possible, and I would say that the charges are on the surface of a conductor. This is not true for insulators like glass, wood, plastic, etc. This is only true for metallic objects like conductors. They are always going to be on the surface because they are free to move. In insulators, they cannot move freely. Okay. Next important thing that you should know is whenever you have any solid part, be it a cavity, without cavity, doesn't really matter, guys. Okay. So what is very important is that once I know that the charges are only going to be on the surface, most important thing, field is never going to be in the solid part of the conductor. It will always be zero inside the solid part. So this entire region, you will see that the field will be zero, but outside of this, you will see electric field lines. You will see electric field lines probably like this. You might see electric field lines like this, and so on and so forth. Electric field outside will not be zero if it is charged. Also, most important thing, these field lines are always perpendicular to the conducting surface, no matter where they originate from. Very, very important. They are always perpendicular and they are only outside. They are never in the solid part or the chunk of that conductor. Keep this in mind. Is everybody okay till here? They cannot go inside, because if they go inside, they will start moving the charges, which will violate the conservation of energy principle. Because charges can't move inside a conductor once it is at rest. It will create current, which will create heat, which violates the conservation principle. One more interesting thing which you should know about conductors is, if you have a sharp edge and a blunt edge, okay, this is sharp, this is blunt. Blunt means it's curved with a big radius. This is sharp, that means the radius of the curvature is small. Here the radius of curvature is large. You will notice that the charges will accumulate in a very different manner. Where it is sharp, you will see a lot of charges getting accumulated here, and here will be very less. Here it will be decent because this is flat. In fact, I would say that here there will be a very, very strong field, something like this. There will be a very, very strong field. Here there will be field, but it will be little bit weak. In fact, the field is inversely proportional to the radius of the curvature. Very important. Wherever the radius is small, field is strong, charges are very densely populated. Where the radius is big, it's a blunt cut. So you will see radius is large. Here charges will be less, accumulation will be less, field will be also weak. Very, very important. I hope this is clear. So very, very crucial pointers related to conductors. Now we will advance more than this, because obviously these are not enough to solve all the kinds of problems. Imagine there is a conductor with cavity. Okay, just imagine there is a conductor with cavity. Then what happens? Let's just try to draw a conductor with cavity. Okay, this is the solid part of that conductor. There is a cavity in it. Just like your tooth can have cavity, even a conductor can have cavity. Now, in such cases, what happens is, if you charge it, the charges always again go on the outer surface. There is no charge elsewhere inside the cavity. So for a conductor, so I will say for a conductor with cavity and no charge inside, the charges spread on outermost surface, on the outermost exposed surface. not on the inner surfaces. There are no charges which you will see on this surface. A lot of people think, oh, this is also a surface, sir, so maybe there will be charges. No, nothing else will be there over there. It will be only on the outermost surface. Not just that, you will also see field lines as usual, only outside, nothing else. Here you will have field lines, here also you will have field lines, that's it. These are all perpendicular. There will be no field inside the conductor or even the cavity. Everywhere, here also the electric field inside will be 0. So the field, I will say, field exists only where? Outside. Only outside. Very, very important. Not inside the conductor. It will not be there because these charges will try to cancel the fields within. It's not that this charge is not creating a field. It is creating, but it is getting cancelled by all the other charges within on the surface of the conductor. So it will just cancel, simply put. Moving on to the next point. What happens when there is a charge inside and what happens when there is a charge outside the cavity? These are two important cases which you should know. Let's start with inside first. So imagine that you have a conductor again and you have a nice cavity over here. This is the solid part of that conductor. Okay, so this is the solid part of that conductor. Great. And let's say somebody happens to put a positive charge, let's say over here. Now there will be a strange phenomena which will happen. Not so strange if you think a little bit deeply. This positive charge will ensure that it pulls the opposite charged particles towards it. Positive is opposite is negative. So what will happen is you will notice some negative charges coming over here. Some negative charges coming here. It is closer here, so more negative charges will be here on this side. There will be fewer negative charges over here on this side. This is how the negative charges will come. Now, if these negative charges have popped up, why did they pop up? Because they are getting pulled by the positive charge. Positive charge will pull all the electrons. If it has pulled the electrons, obviously these electrons would have traveled from somewhere. They would have left somebody. Who they would have left? They would have left the atom. So these negative charges would have left the atom over here. Plus charges, plus charges, plus charges, plus charges, plus charges, plus charges over here. So an equal amount of positive charges developed on the outer surface to compensate. Is everybody clear about this? Why this happened? This is just to compensate the charges, or basically charge conservation. These charges, I'm going to call it as an opposite charge is basically induced on the inner surface, of what? Of the cavity, and you will say outer surface also. You will see charges are induced. These are not actual charges. These have come because of the motion of the charges within the body of the conductor. That's why they are called induced. It has happened because of some external phenomena. It has induced inside that particular solid. Charges are induced on the outer surface by conservation of charge, by conservation of the charge principle. This is how it works. Very, very crucial. Now, what about the field, you might say? Field will be there, but it will be there from here to here because positive is there, negative is there. Yes, you will have field lines over here. Always field lines will be there. Here there will be a little bit less field because charges are less. Here there will be no field because it is the solid part of the conductor. Again, the field will exist outside. It will not exist in the solid part. No matter what you do, solid part can never have any field. So this is how the field looks like. So field is there in the cavity. If you compare it with no charge, notice there was no field inside because there was no charge. The moment you put a charge here, you will see field lines coming up over here. Is that clear, everybody? Yep. So these are very, very crucial pointers for you to solve Gauss law problems, for you to solve conductor problems, shell problems, plate problems, etc. Now what happens when the charge is outside? Okay, let's take that example as well. Imagine you have a conductor, you have some cavity. Okay, this is the conducting part. So this is the solid part of that conductor, let's say. Okay, and now what happens is you take a charge, but it is now outside. Let's say it is over here. What will this do? What will this do? This charge will pull the electrons over here on this conductor. Yes, the negative electrons will come very close over here. You will see negative charges coming over here like this, like this, like this. Yeah, there will be negative charges over here. There is no charge in the cavity, right? So no charge will be induced on the inner surface. Very, very important. If there is no charge inside, no charge is induced on the cavity surface. No charge induced on the surface of cavity. On the surface of cavity. Now, if negative charges have come here, where will they travel from? Think about it. They would have traveled from the other side. So an equal amount of positive charge will be developed. Come on guys, let me know if you guys are understanding this. Let me know in the chat box. These negative charges are coming close. It's like they have left the atoms and come over here because they love the positive charge. If they have left the atoms, so an equal amount of positive charge will be developed on the other side. So this is what happens. So these are basically opposite charge, I will say over here actually, opposite charge induced. Opposite charge basically is induced over here, okay, because of this. And over here, an opposite charge is created. Opposite charge of induced by conservation. By conservation of charge. Conservation of charge is also created. Everybody with me? So this is how it works. You should know all these things. And yep, talking about the field lines will obviously go like this, will go like this, will probably go like this, and so on and so forth. They might also go like this. Some field lines might even come from here. Yeah, some of the field lines will go like this, go like this. These field lines will go like this. Some field lines might just probably end over here. And obviously more field lines will keep on popping up. Everywhere the field has to be perpendicular, there is no doubt about it. Okay, that is standard. So this is how the field lines will look like. These are your electric field lines. There will be no field within the conductor or even in the cavity. Electric field inside, there is no charge inside, there will be no field. As simple as that. Have you understood all the important pointers of conductors and their fields? Very, very important. Solid conductor, where the charges are, how the field is, where is it strong, where is it weak, where is it zero, how is it perpendicular. What happens when there is a cavity and no charge? That's the second case. The third case, when there is a charge inside. And the fourth case is when the charge is outside. Let's solve some questions based on this. Okay, I have put up all the pointers over here also. Here is the question. Come on, answer this question. The electrostatic field due to a charged conductor just outside the conductor is, come on my warriors, figure this out. Just outside. 0 and normal to the surface at every point. 0 inside the conductor and normal to the surface. No, there is no field inside the conductor. So no question of normal. 0 and parallel. No, it's not parallel to the surface. Parallel to the surface, the word only is wrong. It can't be parallel to the surface. Normal to the surface and 0 inside the conductor. Okay, at every point and okay. Now if you notice option A and D, 0 and normal to the surface at every point and inside the conductor, normal to the surface at every point and 0 inside the conductor. There's a small difference. Okay, B option and C option just got eliminated, Setu. Okay, no Aryan, it will not be A, I feel. 0 and normal to the surface at every point. How can it be 0 and then normal also inside the conductor? See guys, if this is the conductor, if it is 0, a 0 vector does not have any direction. A 0 vector does not have any direction. I know it is 0 inside the conductor. How can it be normal? So option A goes wrong. Normal to the surface at every point. Normal to the surface at every point and 0 inside the conductor. Yes, normal to the surface at every point and inside it is 0. So I think it should be option D. Yep, it is option D. So it's just a play of words. If you analyze it in little bit detail, you will get it. Next question. If there is a charged spherical conductor of radius 15 centimeters to a potential V and at a distance of 15 centimeter from its center, then the potential at a point 3 centimeters from the center will be. Interesting question. I think we should draw it, then only we'll get it. A charged spherical conductor of radius 15 centimeter. So this is a charged spherical conductor. So obviously, if it's a conductor and if it is charged, the charges are going to be only on the periphery. The radius of such a conductor is 15 centimeters. At a point of distance 15 centimeter from the center. 15 centimeters from the center, that means it is here only. And what is the potential? The potential is V. Correct? Everybody with me on this? Now, what is the question? The question is basically at a distance of how much? At a distance of 3 centimeter, what is the potential at this point? Guys, the logic for this is very straightforward. Observe now. Imagine this. I know inside what will happen is the electric field is going to be 0. There is no electric field, it's a conductor. There is no field inside, outside there will be field. This point is inside, this point is also on the surface. Okay, great. These are all a part of the solid conductor. If the field is 0, that means dV by dr is 0. Now if dV by dr, rate of change of potential is 0, what does this tell you about the potential? If anybody's derivative is 0, that means that anybody should be a constant function. So hence the potential will be constant. Potential will be constant. What does that mean? That means not just this point, but this point, 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 this point. Every point has the same potential. So there is no doubt about it that this point also has potential V only. Hence the correct answer is option D. Hence the correct answer is option D. That's the beauty of this question. In fact, maybe we should just add this even in our pointers. Maybe over here. Maybe over here. We should probably add it over here. So whenever you have a conductor which is charged, remember all points inside are equipotential. And if you talk about the field line, equipotential lines outside, because I know that the field is perpendicular, the equipotential lines outside the conductor will just take the shape of the conductor. Something probably like this. These are your equipotential lines, V1, V2, and so on and so forth. These are your equipotential lines outside, but inside there will be equipotential volume. In fact, the entire conductor will be at the same potential because there is no field, so potential can't change. I hope this is clear. Mohammed, we will not be starting classes for EMSET on this channel, bacha, but whatever classes you are seeing for JEE and NEET are also applicable for EMSET. It's not like the charges of the conductors or the properties of the conductors or the properties of the field and potential are different for EMSET and for medical and for JEE. So it is the same thing, Mohammed. When you prepare for JEE, you automatically prepare for all the entrance tests. Yes, at the end we'll have mock tests for EMSET, but not special classes for EMSET. There is no point in that. If you are looking for some special class, then I think you are probably looking in the wrong direction. In fact, that is not going to help you for EMSET or for JEE. In fact, I would say prepare for JEE, automatically prepare for everything else. Going on to the next question coming up on your screen. Draw the charge distribution and the fields in the following cases. So let's just I'll take up an example. Let's say there is a charge over here. And I want to draw the field lines on this conducting shell. You can see it has some inner cavity, there is some thickness, and there is an outer surface. Let's try to do this. What will happen the moment you place a positive charge? It will create an induced charge, opposite. It's inside the cavity. So it will immediately ask the electrons to come over here. So you will see a lot of electrons accumulating here, but slowly the distribution will fade away and there will be very few electrons left over here on this side, correct? This is how the distribution might look like probably. Now, because the electrons have come here, what will happen? There will be a field from this positive to the negative charge. They will go like this, right? They will go like this probably. This will be the field lines at every point over here. There will be very few field lines on this side, but wherever they go, they will always be perpendicular. They are bent because they have to be perpendicular at every point. Keep this in mind. So that is why the field lines are bent, and they will always intersect the conducting surface perpendicular. That's the standard property. Definitely got one. Okay. Now what will happen? Okay, this much is done. In this solid part of the conductor, remember the field has to be 0. There cannot be any field in this solid part. Now I know the outer surface will get a positive charge for sure, because these negative charges would have traveled from somewhere. Where will they travel from? From outside. So there will be some traveling happening from outside to inside. So now comes, how will the positive charge outside be distributed? Well, I have a simple point to make. Now the outside charges, you might think, will be accumulated more over here because there are more negative charges. That's not true. Think this way, these positive charges have no way to know where these electrons have gone. Reason being, the field in this region is 0. The outside charges are completely cut off. It's like there is 0 field. No piece of information is flowing from here to here because the field is 0. So these negative charges will not affect the positive charges, because the negative charges field is completely cancelled out by the positive charges field. In fact, they have aligned in such a way that the field in this entire thick part is 0. So there is no flow of information outside. So these positive charges will be like, I don't know what is happening inside. I just know that the field is 0. Nothing is coming from inside towards me. So they will just align themselves symmetrically. So you will see a symmetrical distribution of the charges. That's it. Symmetrical, completely symmetrical distribution of charges. So here the field lines will be just radially outwards. That's all. You will just see radial field outside the conductor. That's it. So this is the best part about the problem, that outside the field distribution is symmetric, but inside it is not, and there is no reason for outside charges to know what is happening inside because the field is completely cut out. So this is how you solve this question. Great. Let's come to the final part of today's session, and that is basically dielectrics. Now, what is this dielectric and what is this permittivity? You will understand it from this part. You might have seen this and how it works. We are going to discuss. See guys, when field travels into some medium, you will see the intensity of the field changes. That's why in the potential energy, potential field force term, you have that constant 1 by 4 pi epsilon. That epsilon depends completely on the medium, because the strength of the field changes from medium to medium, and you will see that the field is strongest in vacuum. The moment it goes inside the medium, it affects the medium, which in turn affects the net electric field. So imagine this. You have electric field moving like this. This is, let's say, E naught. This is field in free space. Field in free space. Very, very crucial. Now this field lines travels in a medium. Now what happens is, a dielectric, basically die means something related to dipole. Now what is a dipole? I'll talk about it. This basically is related to your dipoles. Basically polarities are developed. I'll tell you how. See, in an atom, okay, in an atom you have this nucleus and you have this beautiful electron cloud, okay, beautiful electrons which are revolving around the nucleus. Usually the positive and the negative centers are aligned. It's non-polar. But the moment you apply electric field, what happens is the electron cloud basically shifts. The electron cloud shifts, and you will see the positive charge will be somewhere here and the negative charge will be somewhere here. This is under the influence of external field. What you have seen is a charge separation. You will see a negative charge here and you will see a positive charge over here. So basically what you are seeing because of the external field is a charge separation charge separation in a non-polar medium. In a non-polar medium, that means this was already a non-polar molecule. There were no polarities. Both the centers, positive and negative centers, coincided. Now it was a non-polar. You have polarized it. You have charge separated it by applying some external field. See if this makes sense. Now, sometimes what happens, the molecule is already polar, like H2O or carbon dioxide. These molecules are having their own individual polarities, maybe from one atom to the other between the bonds. So in those cases, what happens is you might have, probably a molecule which already has some kind of a positive charge, and maybe some side is already negative. This is basically a polar molecule. When you apply an external field to such a molecule, what happens is the negative charge gets pulled this way, positive charge gets pushed that way by the field. You will see the negative charge becomes like this, and you will see that the positive charge becomes like this. Okay, they become like this, and this is in the presence of external field. In the presence of external field. So what will happen is the polar molecules align in the direction of the field. Now, be it polar molecules like this or non-polar molecules like this, in either case you see negative and positive aligned in the direction of the field. In both the cases, are you able to see that? Be it non-polar or be it polar, you will see negative positive being separated and aligned in the direction of the field. Now this creates a whole new thing. See guys, with the moment you have a negative charge and you have a positive charge, it creates an electric field around it, and that electric field travels like this. The electric field basically travels from the positive to the negative charge. It goes like this. It goes like this. So what you will see is electric field lines going like this. Okay, in this particular direction. I hope you guys can see this. All right, just let me remove this. Great. Yeah, this is how the electric field lines looks like for basically a dipole, two polarities separated by some distance. Now this creates the whole issue over here. And now that I know that be it polar or non-polar mediums, I know that the charges are separated in the direction of the field. This dipoles create a field which you can see opposes the external field. If external field is like this, these charges are creating electric fields exactly backwards. So what you will notice is that if you have a medium, okay, this is basically a dielectric medium. That means where you can create poles, a dielectric medium, and you notice that you pass some external electric field. Immediately you are going to notice polarities over here. Maybe I can show it in some different color. Maybe I should have shown this conductor only in a different color so that we are consistent with it. Okay, beautiful. Great. So what you're going to see is charge separations happening everywhere. So plus everywhere, and an equal negative charge everywhere throughout the medium, because of which you will see field lines coming like this, 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 everywhere guys. I'm just showing few of them. Okay, like this. These are basically your induced electric field. What is it? Induced electric field. So I can say that the induced field opposes, what does it oppose? The external field inside the medium, because of which if somebody tries to calculate if somebody tries to calculate the net electric field inside the medium, he will immediately say, oh well, I know this is nothing but the, okay, forget the vector sign. Let's forget the vector sign. Yes, the magnitude of that field will be the external field E naught minus what? The induced field. So that's why you see the field inside reduces. Hello Vijay Kumar. Very good, Aarti. Awesome. Did you see this? What just happened? So the charges got separated. Why only positive charges attract? Both negative and positive, both will get repelled or attracted. So what happens is when you apply external field, the positive charge will be pushed in the direction of the field. The negative charge will be pulled in the direction of the field. Both will separate. It's not that only positive will move, both will separate. But the motion of the electrons is more apparent because nucleus is more stable and heavy, and it does not relatively change its position so much. Most of the motion is with the electrons because they are tinier, free to move and easy to change the orbital shapes. Okay, I hope this is clear, Rajkumar. Now, what happens next is very important, that this field is always going to be less than the external field. So like you can see, the net electric field will be less. This net electric field is less than the external electric field by a value of K. This is very, very crucial, guys. You should know this. This K is called as the dielectric constant of the medium. So it reduces K times. If I say K is 2, that means the moment you pass the electric field, whatever its strength, it will become half of it. If I say the dielectric constant is 5, then the moment I pass the field, it will become 5 times less. Usually for ceramics, it lies between like 200 or 300. So it reduces the field strength by 200-300 times. For paper, wood, etc., it might be 5, 10, 15 in that range. I hope this is clear. Pavan, you can leave a comment after the video, maybe I can help you. Now that we have understood how the external and the internal field works, now comes the final part. See guys, in air, the force or the field looks like this. This is in air. In air, be it potential, be it force, anything, it will be like this. 1 by 4 pi epsilon naught, or you can say not just in air, guys, I can say vacuum or basically free space. In free space, E naught will be 1 by 4 pi epsilon naught. You can have a charge at a distance r, so r square. But the moment you are inside the medium, the field in the medium will be, like I told you, it is E naught divided by the value of K. So the value of E naught is nothing but 1 by 4 pi epsilon naught, and I have Q and R square. This K from here just comes over here as it is. These two people I can combine together and I can just write this as 1 by 4 pi. This is the field in the medium, of course. In the medium, I can do the same thing for force. Instead of epsilon naught into K, it's not the Coulomb constant, it is the dielectric constant. I can just put epsilon of that medium and I can put Q by R square. This is the permittivity of the medium. Permittivity. Instead of epsilon naught, you are putting epsilon of the medium. Permittivity of the medium. So basically the permittivity of the medium is nothing but the permittivity of vacuum into the dielectric constant. This is very, very crucial. This is how you can relate. And this is also an important formula. This is the field or force formula for any charge in any medium. Can dielectric constant be 0? A very unrealistic case, or basically a very ideal case, I would say. Okay, so we can have both kinds of extremities, 0 as well as infinity. I would leave it up to you to think what would be the dielectric constant of a medium, and also I would like you to think, can dielectric constant be less than 1? If dielectric constant is less than 1, then that means the field strength will become stronger than the external field. So ideally speaking, dielectric constant should not be less than 1. It has to be more than 1 because the external field is always opposed. So you cannot have K lesser than 1. Okay, I hope this is fine. Let's do some questions maybe based on this coming up on your screen right now. The dielectric constant of a particular pure water is 81. What is the permittivity, guys? Come on, think about it quickly and try to answer. What will be the answer to this? The dielectric constant is 81. What will be the permittivity? The permittivity of any medium is permittivity of free space into K. Now the value of epsilon naught is nothing but 8.85 into 10 to the power minus 12 to 10 to the power minus 12 into basically 81. Let's do the math and you are going to get it, guys. Come on, try it out on your own. You can pause the video and also watch it. Just check it out. If it comes out to be 7.16 into 10 to the power minus 10 SI units or MKS units. Okay, direct straightforward. Just do 8.85 into 81. I think the powers of 10 will also get modified. Okay, moving on to the another question coming up on your screen, and here it is. If a dielectric is placed in an electric field, then which of the following statements are true? You have seen that in the previous years, the statement based questions are very frequent these days. So you need to solve these conceptual theory or statement based questions. The direction of the induced field is the same as that of the direction of the external field. Well, if the external field is like this, I know the induced field is always opposite it. Opposite. This is external. And because of which the remaining becomes the net field. Remember, external minus induced gives you the net field. So now try to cancel out all the options which does not make sense. The direction of the induced field is same as the direction of the external field. Induced same as the external field? No, definitely wrong. Magnitude of the induced field is same as that of the direction of the external field. The magnitude of the induced, how can be same as that of the direction? Does not make sense, guys. The direction of the net field is same as the direction of the external field. Yes, external field and net field have the same direction. So yes, this option is correct. Option C it should be. Option C. Tanya, I'm very good. Okay, very good, guys. For the previous question, you guys have answered very good. Raj, Aarti, Daily Blossom, awesomeness. And this is option C because net field and external field are in the same direction. Induced field will try to oppose the external field. One last question, and let's see how many of you can do this. Charges are placed in vacuum and the force between them is 100 Newton. So imagine there are two charges, okay, in vacuum, and there is some kind of a force between them, and that force is given by 100 Newton, and this is in vacuum. This is in vacuum or free space. Okay, I'm just going to call this as F. Now what happens is you are taking the same charges. But now you are placing it in some medium. Now the moment you place it in the medium, I know what is going to happen. The new force will be different. The force inside the medium will be K times less than the force in air. So whatever the original force was, which was 100 Newton, divided by the K, dielectric constant is 4. So divided by 4. So that means it will be nothing but 25 Newton. So that is the force in the medium. This is on the charges in the medium. Or I would say between the charges. On the charges is not the right word. I would say between the charges. Now the question asked is the force that the medium applies on the charges. Beautiful question. Earlier the force was 100 Newton between the charges in vacuum. When you placed it in the medium, the force just became 25 Newton between the charges. What does this tell you? This clearly tells you there is a reduction in the force from 100 to 25 by 75 Newton. Why has that come? Because the medium has applied that force. So the force that the medium applies, this is by the medium, will be nothing but 75 Newton. As simple as that. Is that understood? Beautiful question. A lot of people leave the answer as 25. No, that's not correct. The correct answer is 75 Newton. I have kept some homework questions for you. You're going to put up the answers in the comment section. So make sure you solve it and let me know in the comment section. And if you guys want to join my batch, there are AI batches which are recorded classes, but all the interactions are live, including hotspot quizzes, class teacher, everything. Or you also have the option of live batches where you get additional benefits of hard copy of the material rather than the soft copy which you get in AI batches. Obviously, the tests, assignments, everything is same. So some additional features are there. You can just go and have a look. There are links in the description box. You can also click over here as well as here for your NEET as well as JEE batches. The batches start for as low as 8,100 rupees, which is very affordable till the last day of JEE or NEET. So all the best teachers are there for all the subjects, be it JEE or NEET. You can have a look at them and make sure that you also see and compare different institutes and what you guys get and what you guys don't get and what you guys need, because you're going to study at the comfort of your home, in the luxury or at your home. So make sure you make the best use of the time that you get and you save from traveling, and also the energy that you save from traveling as well. And obviously the prices are affordable at AI Live Vedantu. Make sure you check them out. Thank you guys very much for having a great and a wonderful time. Make sure you share and like this video. It means a lot, or else I will not be encouraged to conduct more such classes. Okay, so thank you very much. Have a great day. See you next time. Hasta la vista, Captain Shreyas.